Hello, so today we'll be discussing chemical equations and chemical changes and how we might represent them and how we might be able to utilize it for our own benefits. And so we discussed physical changes and chemical changes in previous units. And just to remind you, a physical change would occur if, for example, you take water and you freeze it. That does not change the identity of the substance, and you can easily recover it by heating it up. A chemical change, on the other hand, is something that occurs to a substance to transform it into another. And for example, if you take hydrogen and oxygen, you can mix them together and you can form water if under the right conditions. Water and oxygen gas are not the same thing. They're completely different substances, and you can't recover oxygen out of water. They're just completely different chemical beasts. So a chemical equation is going to represent to us a chemical change. And very simply, mathematically, we're going to identify that as A plus B going into C plus D. And when I say an equation, I do mean it like a mathematical equation. You have that arrow, which acts sort of like an equal sign. And to the left of that arrow, you have what we call reactants. A and B are reactants in this particular equation. And on the other side, on the right side of the arrow, you have the products, C plus D. And now I will just denote that this does not mean that all chemical equations have two reactants and two products. It's possible to have just one reactant and one product, or maybe three reactants and maybe five products. The sky's the limit here. I'm just showing you a generalized thing. You could have A going into B, or A going into B plus C, or something like that. And you will see in subsequent chapters that this acts like a mathematical equation. You can easily manipulate this to get A on the other side, mathematically, of course, not actually in chemistry, but mathematically. You can add two equations and you can subtract equations together, and this acts literally like a mathematical equation. All right? A, B, C, and D are distinct substances, meaning that they don't look or feel or act anything like one like another. So if I were to take A, for example, and heat it up, I will not get B in any way, shape, or form. They're just completely different things. Imagine it's sort of like water and I don't know, ammonia. They're completely two different things, and you can't just get one from the other. All right, so the arrow is going to signify a chemical reaction. We denote the word reaction as RXN very often in engineering and in science. You will see RXN instead of someone writing reaction. I just want you to be familiar with it. I will try my best to keep it to reaction, but if I sometimes in solutions or things like that write RXN, you should know what that is. It just means reaction. And you will typically see that as you go on with your scientific and engineering career. All right. So here is a pretty typical chemical equation, and this is the easiest one to describe. Hydrogen and oxygen come together and they form water, and this denotes this particular chemical change. But some stuff's missing. All right. You will note that on the left side, I have here two oxygens, and on the right side I only have one oxygen. So what we say is that this equation is imbalanced. All right. Additionally, I don't have the chemical states, the physical states, sorry, for these particular species. So is hydrogen here a liquid? Am I forming liquid water? Am I forming gaseous water? It's important to denote in chemical equations what it is you're working with. So this is a good balanced equation that denotes a chemical change. It's telling me that hydrogen and oxygen were gases and I'm forming a liquid. It's also telling me correctly that on the left side I have 4 hydrogens, on the right side I have 4 hydrogens, on the left side I have 2 oxygens, and on the right side I have 2 oxygens. Everything is balanced, everything is happy. This is a very important thing to do when dealing with chemical equations, is to balance them so that you can understand mathematically what's going on and you're not misleading yourself. All right, so let's look at an example of a chemical equation and how you might balance it. And as an example here, I'm having here the combustion of propane, which you do every time you use your cooktop at home if you have a gas top. Let me just we'll do this by hand as well, and later on, just so you know, I have that here step by step solved for you in the PowerPoint, so you can go back and look at it if you don't want to feel like listening to me talk. All right, so excuse me here. So I'm going to have propane here. Sorry, trying to find myself. Make this zoom better. All right. So I have propane, and it's a gas, and it's going to interact with gaseous oxygen, and it's going to form water vapor and carbon dioxide. This type of equation is known as combustion. This type of reaction, sorry, is known as combustion. And we will talk about that in a bit. But basically, anytime you have a hydrocarbon, C and H, maybe CH and O, and you light a match to it in the presence of oxygen, you will form water and carbon dioxide. Okay, and it's known as combustion. So we're talking about combustion engines in cars, or in airplanes, or in boats, or things like that. Typically, it's a reaction like this that takes place when you are burning a candle. You're doing the same thing. You're releasing water vapor and carbon dioxide, we will talk about that in subsequent chapters. But you can have incomplete combustion, in which case you will form other products like carbon monoxide. So this is why you may not want to combust anything in a closed environment. Well, other than the fact that you're going to create some smoke and you can die from smoke inhalation. But if it is uncontrolled, if the reaction itself is uncontrolled, you may form carbon monoxide, and this carbon monoxide is impossible to detect with the human senses, and you can poison yourself and die. So it's very serious. So we will look at how to do this. And so the trick here is that it's trial and error, as you may have seen in the slide. And what we'll typically do is, for your own bookkeeping, and as you get more and more well versed in this, you may skip this if you want, but I'll just do this for you right now. I have three elements I gotta worry about: C, H, and O. Okay. And I have this side of the equation, right here, the left side, and I have the right side of the equation. And I'll just kind of like play around with it until I get it. There's no systematic way of getting it right. Very often, to this day, I just kind of just do trial and error, and I get it when I get it. And you just kind of just make sure that everything is balanced as you're playing along with it. So first thing that I'll do is you will note that on the left side I have 8 hydrogens in the propane, and on the right side I only have 2. So to rectify that, so I'm going to write that. So on the left side, let me just write everything. On the left side I have 3 carbons, I have 8 hydrogens, and I have 2 oxygens. Oops, not 0, 2. 2 oxygens on the right side. On the left side. On the right side, I have 2 oxygens from this and 1 oxygen from this, so I have 3 oxygens, right? Oh, that little symbol is annoying, right? The hydrogens here, I have only 2, and carbon, I have 1, right? So right away you can see I need to balance all of them. So in order for me to do that, like I said, I'm going to just pick something and go with it. So I notice that my hydrogens are imbalanced. I have 8 on the left and 2 on the right. Fine. So I will put a 4 here. Okay, if I put a 4 right there, you know what, I'll do it in blue. If I put a 4 over here, okay, now I have 8 hydrogens. Yeah, I still have, my carbons didn't change, I didn't play with it, but my oxygens did. So now I have 4 oxygens plus 2, I have 6 oxygens. Okay, just so we're aware that this is happening. Okay, so that's my first change. Nothing changed on the left side, I didn't play with it, I didn't put anything. All right, now I get to go with something else. So let me pick on, I don't know, carbons. Okay, so I have 3 carbons on the left and I have 1 carbon on the right. So I could just put a 3 in front of the carbon dioxide here, 3 right here, and so now I will have 3 carbons and 3 carbons here. That's cool. I did not mess around with my hydrogens, as you notice, so I still have 8 hydrogens, so that's cool too, so they're balanced. But now I have, let's see, 6 oxygens and 4 oxygens, that's together 10, and I only have 2 on the left side. Well, now I can easily fix that because I have 2 on the left side and oxygen is by itself. I can just stick a 5 right here, and now when I stick the 5, this will become 10, 8, 3, and everyone here is balanced, and my balanced equation will look like this. Plus 5 oxygen. I just omitted the states, but I just want to show you mathematically what's happening. It looks like this at the end. Okay, and the correct answer would have the states. You know, gas, 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 gas. I just omitted it just to show you the numbers. All right. So a few take-home messages here. 1. You can only play around with the coefficients. I cannot, and will not change the subscripts. If I were to change this 3 here to a 4, this becomes butane. That's not propane. If I had to change this 2 to a 3, it becomes O3. That's ozone. That's not oxygen. So I cannot play with a subscript because they denote a chemical species. But I can tell how many of them I have. Okay, it's sort of like, well, I have 1 propane molecule, 5 oxygen molecules. They will react together to form 4 water molecules and 3 carbon dioxide molecules. That's how that would work. Okay, it's just like a counting type thing. Okay, so hopefully that makes sense. The other take-home message I want to convey here is, you noticed I seem to willy-nilly, if that's a word, willy-nilly. I seem to just willy-nilly pick a hydrogen first, and then I picked carbon, and then I picked oxygen. I had some method to my madness. I saw that oxygen here is by itself, and I saw that here it's coupled with the other 2. And so I figured, you know, if I were to mess with oxygen right away, I have to go back and forth a whole bunch of times. Hydrogen is only in water and only in propane, not here and not here. So if I play with this, I will fix my hydrogen. That's why I picked hydrogen first. Same thing with carbon. Carbon is only here in the CO2 and in the propane. It's not in the water, it's not in the oxygen. So it's much easier for me to just play with that. And then at the end, I can do oxygen, because that's the only thing that's left, and it's its own little thing. Okay, so hopefully that made sense. And like I said, I promise you that I have the exact same thing. I just verbiaged at you, denoted here 1, 2, 3, and step 4 is yay. All right, so a balanced equation right here. Other things I want you to note, that just like math, it's an equation. If I have everything doubled, it's the same. I can divide through the entire thing by 2. It doesn't make much sense to denote 2a plus 2b goes to 2c plus 4d. I can just simplify that. So we're going to simplify all of our equations just like mathematics. And let's go over some simple chemical reactions you may see. These are called combination reactions, when I have A and B forming this thing called AB that looks like AB got together combined. So examples would be sodium and chlorine will form sodium chloride. or carbon and oxygen forming carbon dioxide or carbon monoxide or things like that. Whenever you have something that's an A, something that's B that are unrelated and they smush together, you're gonna find these combined. The opposite is known as a decomposition reaction. Okay, and here are some examples. You can easily reverse these. These will be decomposition. If I take NaCl and I somehow decompose it, it will form Na plus Cl2. Yet other examples would be here. So, like for example, sodium azide here will form sodium and nitrogen gas. Okay, not N3 or N2, but whatever, it doesn't really matter. I'm taking an Na and I'm separating the Na out and I'm separating the N out. So that's a decomposition. This is a combustion reaction. So I told you already, we talked about that a little bit. These are hydrocarbons and these are with oxygen as well. X, Y, Z denote any number you want, any ratio, whatever works. And so if I were to expose these things to oxygen in the presence of fire, I will always form carbon dioxide and water if it is a complete combustion. And here are the examples. One we just balanced, and another one here with methane combustion will form the last equation, right? So now we'll talk about percent decomposition.